Okay, so now we know what a public key cryptography is. We talk about hard problems. We talk about algebra. Now we can actually come to discrete logarithm problem because this is defined on a group. So let G be a group and small g its generator. Given A, it should be feasible to compute G to the A. By G to the A, I'm meaning applying the group operation A times to the G. Here I'm using the multiplicative notation. But given B, which equals to G to the A, it should be computationally infeasible to find A. That is, the attacker knows B, they know the G, they know the group operation, but they don't know A. So getting A from here should be hard. And actually it is hard. This is what we are claiming. But the hardness of this interactability, by hard, actually the real mathematical definition would be interactability. But the interactability of the discrete logarithm problem actually depends on the group you are working on. So on some groups, this problem is easy to solve. And on some groups, it is hard. Actually, this will lead us to the elliptic curves, because on elliptic curves, this will be harder. Okay. So let's see some examples. So here I will focus on not the discrete logarithm problem, but the logarithm problem itself. So let's focus on a group which is infinite, not a finite, right? Like rational numbers. And addition is our group operation. So here the logarithm problem is as follows. You are given B and G, and you are asked to find A such that adding G A many times to itself gives you B. So you are asked to find A. So A times G equals to B under this group operation. So this is easy to solve because you can divide both sides by G. So A is turned out to be B over G. Like logarithm problem here is easy. Consider real numbers. The problem here, and this time let's consider the multiplication. So your aim is to find A such that G to the A equals to B, right? So you can choose large numbers like G and B, but at the end of the day, the solution is easy because you can calculate the logarithm of both sides to the base G, right? Because if you do that, left-hand side ends up with A, because log to the base G of G to the A turns out to be A. So all you need to calculate log to the base G of B. So with a single logarithm operation, you solve this. This is why we call it the logarithm problem in the first place. But let's focus on finite fields, finite groups, sorry. Let's focus on ZP and addition. Now your problem is given B and G. Your aim is to find A such that A times G is congruent to B modulo P. Now, due to modulo P here, we are actually hiding our steps here. So this is harder than this problem now. Because here I could divide both sides with G and obtain A, right? Here I cannot do that because I kind of hid my steps by performing the modulo P operation. So this is why we call it an intractable operation. But the thing is that here this is discrete logarithm problem, but the group here is not that hard. So the group doesn't make this problem hard. So for instance, easier way to solve this, multiply both sides by G to the minus A, which is inverse of G modulo P. Because if you multiply both sides with G inverse times G is the identity element, which is 1. So this cancels out. So A becomes congruent to G inverse times B, right? So of course, here the question is it easy to find the inverse of G? And the answer is yes. You can easily compute it by using the extended Euclidean algorithm. So as you can see, the discrete logarithm problem here is not that hard. I can easily solve it. This is why we said that it depends on the group. But if you move on to multiplication group, again with ZP, now the problem turns into given B and G, find A such that G to the A is congruent to B modulo P. And best known algorithms to solve this problem is sub-exponential with respect to P. This is why we are using these algorithms in real life. You don't have a polynomial time algorithm to solve this. Okay? An example is here. I choose 3 as G. I choose a secret number X. Calculate that power with respect to this modulus, and this is a prime number. Actually, the first prime number larger than this 1 trillion, I guess. So this is the result. Question is, can you find X? If you do it by trial and error, you have to try every X one by one. So this is an exponential time solution. but we have sub-exponential algorithms that solve this problem faster. But the answer is here is not that hard. You can solve it. But think about this way. In real life, we are dealing with numbers that are hundreds of digits, not small like this. Okay. So I claim that this problem is harder on elliptic curves, and we will talk about elliptic curves next time. But the points on elliptic curve with a special operation actually defines a group. Okay. So the elliptic curve discrete logarithm problem will turn into the following. Given an elliptic curve E defined over a finite field FQ, a point P on this elliptic curve, where the coordinates are on FQ, of order n, and the point Q such that point Q is obtained by adding the point P itself d many times. Your aim is to find d. So here the problem is modified. So you know the point P, you know the point Q, but I obtain the point Q by adding the point P to itself d many times. So there is a group operation called point addition, okay, which is not simply adding the coordinates, by the way. It is a special operation. So now your aim is to find the, if you can solve this problem in a very fast way, actually you can steal everybody's Bitcoins or Ethereums, okay? So discrete logarithm problem security depends on the group size. So polar draw algorithm can solve discrete logarithm problem in about square root of P times Q over 2, if you are working on the group of FQ, for instance. Index calculus algorithm can solve discrete logarithm on ZP with sub-exponential time complexity. Okay, so this is why we prefer to use elliptic curves. Index calculus algorithm uses relation between small primes, which is not applicable to elliptic curve discrete logarithm problem, because when you deal with integers, they have properties like being prime or being small. But when you focus on points on an elliptic curve, you lose these abilities. This is why a group created on an elliptic curve is kind of better. Thus, using elliptic curves allow us to work on groups with smaller number of elements. This is why in RSA, you have to deal with 3000 bits of secret key, but with elliptic curves, you deal with 256 bits secret keys. So now that we know the discrete logarithm problem, we can now explain the Diffie-Hellman key exchange, because the security depends on the discrete logarithm problem. Let me give you the pseudocode. A and B, Alice and Bob wants to communicate, and actually they want to exchange a secret key. Alice picks a random number A, sends G to the A to the B. So Alice simply calculates G to the A. So G is the generator of the group, okay, and sends it to B. B similarly picks a random number B, calculates G to the B, and sends this number to A. Now, A received G to the B, but Alice doesn't know what B is. But small a is randomly chosen by Alice, so Alice can calculate the 8th power of the number she received from Bob. So she ends up with G to the A times B. Bob does the same thing. He received G to the A from Alice, and he knows what the small b is, calculates the bit power of this group element, and ends up with G to the AB. Now they agreed on a number. Both of them didn't know beforehand, but now they can use this number as an AES secret key, for instance. But of course, this number might be large, for instance, maybe 5,000 bits. They will say that let's use the leftmost 128 bits as the AES key. And this is actually how you communicated a lot in the past when you visited some web pages or visited your banking or e-commerce sites and so on. So let me show it on a picture. Here we're focusing on the field where we focus on ZP, and the group operation is multiplication. So Alice randomly chooses a number, calculates G to the A modulo P, and sends this, we represent it with capital A, sends this to the Bob. Bob calculates G to the B mod P, calculates capital B, and sends this to the Alice. So anybody who is listening to this communication, they know public parameters like the generator element G. They know the modulus P here. They now capture A and B, but they are in this format. So the person who listens to communication has to capture either small a or small b. But in order to do that, they have to solve the discrete logarithm problem. This is why this key exchange is secure. If a person who listens to this communication can solve this discrete logarithm problem, they will capture small b. So they will take the bit power of this and end up with this secret key as the both communicating parties. So this is very, very important. Similarly, we can define an encryption algorithm using discrete logarithm problem. I mean, relying the security on the discrete logarithm problem. This is referred to as ALGAMAL encryption scheme. So in the key generation, what you do is as follows. You randomly choose X. This will be your secret key. You compute G to the X and end up with Y. This will be your public key. And this is as simple as that, okay? Public is Y, private key is X. So when somebody wants to send you a message, and the message is M, they choose a random R, they calculate G to the R, and also message times Y to the R. So G is the group generator G, which is publicly known. R is random number chosen by the person who wants you to send the message. Message, again, chosen by themselves. And Y is your public key, right? They calculate the R power of it. So these results are referred to as UMV, and they send you UMV as the message. What you do is as follows. You multiply V with U, but you take the minus X power of U. And this will gives you the M. You might ask me why. Actually, think about what U is. U is just this, right? If you take the minus X power of it, you end up with G to the minus XR. If you multiply it with this, Y to the R is actually G to the XR. So they cancel each other, end up with M. Simple, basic number theory. Very nice idea. In order to break the system, you have to break this discrete logarithm problem. Yep. Let me show you a final picture. So we talk about many things in symmetric crypto, hashing, public key algorithms, but let's focus on their security when they are combined together. Because in a system, you are going to use a block cipher, hash function, and a public key algorithm. So the smallest security of these algorithms will be your main security, right? So if you want 128-bit security, so this is what we suggest for personal use, you can use AES 128. But if you want to use RSA, like algorithms where your security depends on factoring, the factoring modulus has to be 3072 bits. But if you use a discrete logarithm type security like ALGAMAL, your key has to be 256 bits, but your group size, again, has to be 3072 bits. So in the previous picture here, if you are using ZP as the multiplication, not elliptic curve, but ZP itself, this will be your group size. But instead, if you use elliptic curve as your group here in the ALGAMAL, all you need is to work on values of 256 bits, okay? This is the nice thing. So, but if you want more security, especially if you want to hide government secrets or if you are military, we always suggest that you should use 256-bit security. So if you aim 256-bit security, your AES should be using 256-bit secret key. Your hash function should be SHA-512 or maybe SHA-3-512, nothing less. But if you are going to use RSA like algorithms or groups, then your group size should be 15,360 bits. So in the field, I never seen anybody using this. Even in certificates, you can see RSA 2048, which actually gives you 112-bit security, which is just on the edge. But elliptic curves saves you the time, and it gives you 512-bit security. I mean, you choose your secret key is 512 bits, but it gives you 256-bit security.